Welcome to episode 93 of the Energy Balance podcast, where we teach you how to live without constant hunger and cravings, fatigue, brain fog, poor sleep, and other low energy symptoms by maximizing your cellular energy. I'm Jay Feldman. I'm a health coach and independent health researcher, and joining me again today is my good friend Mike Fave. Mike and I have been studying health and nutrition together for a long time now, and Mike also draws on his experiences from working within the healthcare industry. In today's episode, we'll be going through a study. We'll actually take the next two episodes, and it will be a study that goes over the effects of stress on our mitochondria. And more specifically, we'll be talking about why stress is not your friend, the effects of cortisol on your mitochondria. We'll be talking about Selye's general adaptation syndrome. We'll be discussing how cortisol causes mitochondrial dysfunction, heart disease, insulin resistance, autoimmunity, allergies and hypersensitivity, mineral imbalances, and cancer metabolism, as well as why acute stress does not lead to improved health via hormesis. If you are new to this podcast, then after listening through today's episode, I'd highly recommend you go back and listen through episodes 1 through 7, where we took some time to build a foundation as far as the bioenergetic view of health is concerned. To check out the show notes for today's episode, you can head over to jfeldmanwellness.com/podcast, where you can take a look at the studies and articles and anything else that we reference throughout today's episode. And if you are dealing with any low energy symptoms, maybe these are symptoms that you've been trying to rectify or improve by using some amount of stress through hormetic means, whether that's exercise or fasting or caloric restriction or cold thermogenesis, cold plunges or ice baths or other things along those lines. Maybe it's supplements like resveratrol, or maybe you've been looking to improve these symptoms through other means and haven't had success. This could be symptoms like chronic cravings and hunger, low energy or fatigue, chronic pain, weight gain, digestive symptoms, brain fog, poor sleep, hormonal imbalances, or really any other low energy symptoms or chronic health issues. And so if you are dealing with any of these symptoms or conditions, I'd recommend you go over to jfeldmanwellness.com/energy, where you can sign up for a free energy balance mini course, where I'll explain how these different symptoms and conditions are really caused by lack of energy. And I'll also walk you through the main things that you can do from a diet and lifestyle perspective to maximize your cellular energy and resolve these symptoms and conditions. So to sign up for that free energy balance mini course, head over to jfeldmanwellness.com/energy. And with that, let's get started. All right, so we're going to be discussing a study titled Mitochondria as Key Components of the Stress Response. And the reason why we want to discuss this study is because it's basically a pretty good summarizing type article discussing the interplay between energy production, energy availability, energy balance, the things that we talk about all the time, and stress, and how we adapt to stress through these energetic means. And they discuss it through the terms of the mitochondria. And it ties together a lot of different pieces of the bioenergetic view and digs into hormesis a little bit, which we've talked about a lot. And very high level processes here that dictate our physiology and that is involved in every single disease process, that, the things that we talk about all the time. So yeah, it's a pretty helpful study to go through. And it essentially depicts, again, our response to stress, our adaptation to stress in terms of energy. And so just to start, before we dig into the study, it's helpful to look at the general adaptation syndrome, which was illustrated by Selye, and basically describes our response to stress more in a high-level fashion. And then the study will go into the details of how these things happen. But so it's helpful to get an idea of general adaptation syndrome prior to going through it. So I'll pull that up right now. And so here you can see the three phases of the general adaptation syndrome. We have the first stage, which is called alarm. Then we have resistance, and then exhaustion, which can also be recovery depending on the organism's response. And so you kind of see the two diverging arrows here at the end of that, in that third stage, which is going to, again, depend on the physiological state, how much energy is available, and whether this is, the stressor that the organism is experiencing is that last stressor that's going to lead to, as they depict, severe illness or death. But to kind of talk through these three stages, the first one that we have is alarm, which is our body's initial response to a stressor. So we experience any sort of stressor, and we've defined this before, but just to explain, a stressor is anything that increases the usage of energy, requires the usage of energy. So it can be exercise, it could be an infection, an infectious agent, it could be a heavy metal, it could be ionizing radiation, it could be psychological stress, anything that's going to increase the usage of energy on a systemic level or on a local level. And that's a stressor. And so the reason why it's called a stressor is because it has the capacity to cause stress. And so the initial thing that happens is that if the energy required to handle that stressor is greater than the immediate amount of energy we have available, we hit this alarm stage, which we're kind of seeing here as this curve dips. That's showing that we're in an immediate energy deficit. And the response that our bodies have is the resistance phase. And that's where we respond with stress, the stress processes, where we have increases in the various stress hormones, things like adrenaline, and then later on cortisol. But there's other hormones that are also involved here throughout the RAS system. And you also have growth hormone, glucagon, and things like that, that all kind of have different stages throughout this response to the stressor. And some of them are specific to certain types of stressors. But that's going to be the alarm phase, the resistance phase. And that's going to upregulate our body's defenses to whatever stressor we're experiencing in order to deal with it. And that's what allows us to handle anything that requires greater energy than we have available at the time. And then once the stressor stops and we've effectively dealt with it, then we have that third phase, either the exhaustion or recovery phase, where we're left basically making up for the debt or deficit that we've created by using the stress hormones. And so you could kind of think of it as those stress hormones are basically taking a loan out in order to deal with the immediate energy demand, and then that loan has to be paid back. And that's kind of the recovery phase. And if we are degenerative to the point, and this has happened enough times to where we can't properly pay back that loan, then we start to severely degenerate, and that's when you start to see illness and death. And so that's basically the kind of overview that Hans wrote out, and we'll be talking about the details throughout the response to stress in terms of the detailed physiology as far as how each of the stress hormones are working, or at least some of them that are explained in the study, and what the mitochondrial response is during these different stages, and then the effects that can have. But of course, we've talked about this in terms of hormesis, where when you are there's this confusion, we'll dig into it more, that the resistance phase, where you have all these stress hormones, you have all these adaptive responses, is actually beneficial to induce. Not that it's beneficial to deal with the stressor. Of course, we need it to deal with the stressor, but the idea behind hormesis is that it's good to be inducing that, and that increases your defenses. But of course, there's a cost there that we've talked about in that hormesis series, which I'll link to. But we'll talk a little bit about that here in terms of the effects of the stress hormones. And I'll let you go, Mike, if you have anything to add in terms of general adaptation syndrome.
Yeah, I just wanted to highlight here that, a couple things. So the first piece is, when you have a stressor applied and you're in the alarm stage, the reason we see this initial dip here is because that stressor is taxing the body's current level of energy, or the current energy output. So you see a dip here in the curve there, as the body has a lag time for when it has the stressor, recognizes that there's an increased energy demand, and then it starts to mobilize those resources. And then the mobilization of the resources comes through the adaptive hormones, or the stress hormones. And the reason they're called adaptive is because they allow us to adapt to these increased energy demands. And the main stress hormones, your catecholamines and your glucocorticoids, are literally, their function is to provide energy within an energetic deficiency. The catecholamines, like adrenaline, noradrenaline, those are the two main ones, will essentially cause a breakdown of glycogen inside muscles and inside the liver, and then also release of free fatty acids. So it's releasing energy stores to be burned. And then the glucocorticoids do similar things. They also release amino acids and increase gluconeogenesis at the liver. So in this alarm stage, what you can see is the activation of the fight or flight response, which is the early stress response. And essentially, you have a strong increase in the catecholamines and an increase in the glucocorticoids. And as we go through this extended resistance phase, we'll see a maintenance of the catecholamines and perhaps a little bit more increase in the glucocorticoids like cortisol. And then that's the resistance, because those hormones are essentially releasing energetic substrate that can be burned by the mitochondria. And this is why the mitochondria are so important. And this is why this article is so important, is because there has to be adaptive changes at the mitochondria to basically throttle that burning of energy. So you have these hormones that release the substrate, and then they also have effects that we'll talk about on the mitochondria to increase that mitochondrial burning of the substrates that's released to create an increased energy production under the stressful situation. Now, this next part here, the exhaustion, it doesn't always have to be exhaustion, as Jay mentioned. It can either be exhaustion or it can be recovery. Because anytime you have a situation where you, for example, exercise or some type of troubling emotional or psychological situation, trial, whatever it is, that those situations are going to require an increased energy demand. You'll get a momentary spike in glucocorticoids, catecholamines, depending on the strength of the response, and depending on the length of the response, you may see differing amounts of those different hormones, right? If it's a shorter, quick type of response, I think when we were talking about it, Jay, we were talking about like when you get pulled over by a cop, you may have a brief, or like you see the sirens behind you because you were speeding, which, we don't speed, we're upstanding citizens, but when you see the sirens behind you, you get that fight or flight response. You get that adrenaline rush. You may not need a glucocorticoid release. You may not need a massive spike in cortisol. Just having that momentary adrenaline response covers that deficit, and then you come back to baseline as far as your energy demand. And then essentially, when you go and eat or you rest afterwards, you have some carbohydrate or something. Your response, the stores that you just burned through with that adrenaline response, that fight or flight response, gets recovered, and you don't have so much damage to the body, right? You have that fight or flight response, you get pulled over, yes, officer, yada yada, here's my license, whatever, you're fine. You have your orange juice in the cup holder next to you, which I know all of you do. And then you take a sip of orange juice, and then you can start to recover from that response. Now, so that would be like a recovery stage. Now, something to keep in mind is if you put this on larger time scales or cumulative effects on a time scale, if you had like that happen continuously, you could start to move into an exhaustion stage, even though the stress responses were pulsed. So you could have, you're about to get pulled over, pulsed fight or flight response, and then you aren't able to effectively recover. You have it again, pulsed fight or flight response, and maybe that next time is a fight with your significant other, or something about your rent. Like, these things can become cumulative, and then you can start to see like this curve would change a little bit, so you wouldn't fully recover. Where you see that on the back end of the curve, you see this this piece here, maybe you don't fully recover, you don't come to that blue baseline, you sit just below it, you have that response again, and then you would have the same curve again, but now you'd be starting at a lower point, and then you can continue down in a stepwise fashion, so that you can put it on like a multiple incident type of thing versus just one incident. Now, with the exhaustion, and that can still create exhaustion over time because you continually start at a lower set point. But the next phase that you have here is with exhaustion is if you have a massive stressor, say, for example, a divorce. You have a divorce that goes on and drags out for years and years and years. You have this chronic elevation, perhaps, of glucocorticoids and the catecholamines over time, going to the deal with lawyers, yada yada, court, whatever it is, the pressure of payments, whatever the deal is, and then eventually that degrades the body's ability to deal with that stressor over time, because when you chronically upregulate these compounds, there's only so much resource, so much substrate that you can release over time, and that you can also replenish in a given amount of time. And there's also only so much throttling the mitochondria can handle. You essentially redline the mitochondria over time with glucocorticoids and catecholamines. You're too much pressure on these systems, and then they'll essentially start to break the systems. The mitochondria start to degrade, and then that's what the article will talk about in a second. And that's when you start to see this illness, where over time the structure of the body is degrading under the pressure of the stress demand. And then obviously at an extreme level of this, you see death. So what I'm doing here is I'm taking Ray's hypothesis of energy and structure are interdependent at every level, and then I'm grafting that inside Hans Selye's perspective of general adaptation syndrome, and basically saying that over time, an increased energetic demand over and above what the body has at a normal baseline will throttle up the adaptive stress hormones, and the adaptive stress hormones will initially you can meet the demand, but over time they deplete the body's stores, and then they cause damage to the body's structure, and then that impairs the ability of the body to produce energy over the long term, and then that's when you start to see illness and then eventually death. And then what we're going to talk about today with this study is the effects of this inside the mitochondria. What does this look like at the mitochondria? What does this look like at the engines of our cells?
Mm-hmm. Yeah, and just to clarify a couple of things. So the situation of exhaustion and continued stress that leads to degeneration is not just based on the number of stressors or the amount of stressors, but also our ability to recover from them and our energetic supply or energetic capacity in the first place to maybe even prevent this from happening at all. So for example, if we're here when the stressor hits and there's room within this blue line here before you dip down and actually have to activate stress. And that's the amount of energy we have at the time. And so if we have a lot of energy at the time and the stressor is mild, we might never even dip below. We might never have to activate the stress hormones. Or if the stressor is still is great enough to activate the stress hormones and dip here, but not so much, it might be much less of an increase in stress hormones. And along the same lines, if we again have a lot of substrate available, we don't have things blocking our energetic production in the mitochondria, and on, then it would require way fewer stress hormones and way fewer amounts of them in order to get up to this point to resist the stressor. So this situation could involve huge amounts of adrenaline and cortisol if you're already in a relatively degenerated state, a relatively already exhausted state. Or it might require very small amounts if you're not in that state and you're in a good spot metabolically. So we've got the two sides here. One is the amount of stressors coming in, and the other is where we're at metabolically, so that we can deal with those stressors and have fewer stress hormones, better resilience, and less activity of the stress pathways in the first place, and then also quicker recovery as well. So we want to make sure we're considering both sides. When it came to Hans Selye's view, he viewed adaptation energy, is what he called it, as fixed. So he said that there's only one side to this equation, and it's the amount of stress. And you just deplete your levels of energy more and more and more, and then you get to a point where you degenerate. And so that is a distinction I want to make, that we don't subscribe to that idea that this quote unquote adaptation energy is fixed, but rather that our physiological energy production is not fixed and can be improved or supported or increased basically indefinitely to deal with an unlimited amount of stress if our conditions were absolutely perfect, which of course doesn't actually exist, but the closer we get to that, the greater capacity we'll have. So that was the first point I wanted to make there. Do you have anything to add on to that, Mike?
Yeah, I want to give two things. So the first one is a quick example of what you said. So that, like, an everyday example for people, right? So it's like, if you went to go do a workout and you slept 8 hours that night and you ate really well before, you're probably going to you're more likely to have a better workout. And say you everything's great at the house, right? You're going to get along with your family. You're probably going to have a better workout than if you were to have not slept 4 hours and was kind of poor and had fasted, then a long-term fast, and then got in a fight before that workout. Your power output, all these types of variables would probably be improved compared to the other situations. So that's what that's what you're talking about in regards to ability to adapt to stress and recovery and resting state affecting the response overall, what your current state is in general. And then the next thing I wanted to say is that I do think that there is a point, and they'll get to this. We'll talk about this more specifically in the study, but I think there's a point where if your general metabolic state is quite low and you're exposed to extremely strong stressors, that you can create some damage in the system that can make it very difficult to get back to those baselines. Some of those examples could be sepsis, could be traumatic injuries, things like that. And we'll talk about that specifically inside the the paper, but there's a lot of damage has to accrue before that becomes like a significant deal. But I think that it is possible that if you're in a really low state already and then you're exposed to a very strong stressor, you can create enough like physical damage to the structures inside your body that can impair you like going forward down the line. So, but it is important to keep in mind it's a combination of both factors. What is your external stress applied? And then on top of that, what is your internal ability to deal with that stress? And a lot of times, your internal ability and the external stress applied are related to each other, because if you manipulate your environment to keep a lower external load of stress while providing factors that support your internal load of stress, you can effectively minimize the stress, like the effects of stress on the body to a large extent. So there's multiple things to adjust there. It's not just this external load, and you have to just constantly minimize the external load, et cetera, et cetera, et cetera.
Right. Right. And there would be external stressors, things that cause stress. And you're saying internal load of stress. I think you meant like capacity to deal with stress or resistance reserves. Yeah. Yeah, for sure. Yeah. Not actually wanting to cause stress internally.
Yeah. No, that was counterproductive.
Yeah. Yeah. The other two things I wanted to mention. So just now you were talking about exercise. Prior, you were talking about two examples with like police pulling you over and then a divorce. And those are both psychological stressors that are stressors. But I just wanted to highlight also, because it's something that people are always confused about, is that stressors, there are also physical stressors, chemical stressors. It's not just psychological. So exercise was an example you gave. I know I mentioned earlier, heavy metals, ionizing radiation, various pollutants, all sorts of things. Basically anything that's going to deplete energy is a stressor. And that includes psychological stressors. There's also tons of other different types of stressors. And then the last thing, you mentioned that you mentioned calling the stress hormones the adaptive hormones because they help us adapt to stress, which of course they do. I just wanted to mention that that's not a term that I like, because I consider, again, there's this notion that we only adapt toward stress, but we don't. We adapt toward improved energetic capacity as well. And I'm not saying you're saying this, but just that term might suggest it to some people. But we adapted both ways. We adapt toward really energetically favorable low stress environments. We might do that with increased levels of thyroid hormones or sex hormones, and those continue to support our complexity, and those are also adaptive. And we also adapt to stress with the stress hormones. So yeah, I view all hormones as adaptive. It basically is our means to adapt to any situation, and they just all signal different things, which is their whole point, is messengers, things that signal based on what the environment is giving us and where our internal environment is.
Yeah, no, I don't have anything to add.
Perfect. So I'm going to pull up the study. All right. So the study, as I mentioned, is titled Mitochondria as Key Components of the Stress Response. And it's not a particularly long study, but one that is dense with good information, a lot of good things to discuss here. Basically looking at how environmental stressors relate to, or the response to environmental stressors occurs in relation to mitochondria, and then how that can relate then to degeneration or health on the other side as well. All right, so we'll dig in, and they're kind of talking here about the first phase of the stress response being the acute response. So they say the acute response to stressful stimuli is characterized by release of stress mediators, including corticotropin releasing hormone, adrenocorticotropin, glucocorticoids, and the catecholamines, adrenaline and noradrenaline. In inflammatory stress, pro-inflammatory cytokines such as tumor necrosis factor alpha, interleukin 1, and interleukin 6 are also secreted. And these are, just for anyone who's wondering, these are markers that are used in all sorts of different studies for inflammation, and the prior ones as different levels of stress, something we've talked about before, going through various studies. And certainly, this just helps put them into context. The synchronized interaction of stress mediators serve to 1. Maintain effective blood supply and hence oxygenation and nutrition, primarily to the brain, cardiac, and skeletal muscle. 2. Increase energy production through recruitment of substrates, which is glucose, fatty acids, and amino acids, from body fuel storages, such as the liver, adipose tissue, and skeletal muscle, and enhanced hepatic gluconeogenesis. And 3. Optimize ATP availability to vital tissues at the expense of others, such as the gonads and GI tract. I think it's probably worth pausing there for a second before going on in this quote, because there's so much there in discussing the three main things three main goals that they're kind of describing here of the stress hormones. And one is maintaining circulation. And so this is something we've discussed before, where carbon dioxide is kind of like the equivalent of thyroid or reproductive hormones, in that it's the pro-complexity, anti-stress, or non-stress version of vasodilation and increasing circulation. And when we're under stress, we need to go through backup means to do that, because of course, if we can't get blood flow and circulation to these different areas, they can't function. And so the brain, cardiac, and skeletal muscle being the main ones that are getting that blood flow when we're under stress, and that being mediated by these hormones and other factors. The second being increasing substrate release. So they mentioned glucose, fats, and amino acids. I know you mentioned those before, Mike, from the fuel stores, and also through conversion at the liver. And then last is increasing energy, increasing ATP availability. And they mentioned two vital tissues at the expense of others. And the others that they mentioned are the gonads and GI tract. And so this is something we've talked about quite a bit as well, where when we're relying too heavily on these stress pathways, we end up causing various GI issues. We talked about it in long distance endurance runners, for example. And you also end up reducing the production of steroid hormones at the level of the gonads. And so they discussed that as well. And that being, these stress hormones, these mediators, being one of the main things that turns off our sex hormone production, and something I've talked about in the past as well, in terms of high carb versus low carb diets, or low carb diets, because they drive stress like this, are really good at turning off sex hormone production. So I think it's, I like what they're discussing here. I think it's very clear.
Yeah, and I think there's, I see this directly in an ICU. I see this with when they use synthetic drugs that are agonists or analogs of glucocorticoids or catecholamines. So for example, for number one, for the blood supply, and when you're in the ICU and you have septic shock, one of the things they give you are vasopressors. Some of those are synthetic catecholamines, like norepinephrine. There's also vasopressin. There's Levophed. These drugs, basically what they do is they cause vasoconstriction, but they increase the blood flow to the internal tissues, like they're saying here, your brain and your heart and your some of your muscles, while they decrease blood flow to other areas. So those other areas include your peripheral tissues. So for example, a side effect of incorrectly running pressors or using too much pressors in people, if they have chronic situation, is necrosis of the fingers and toes. So it decreases peripheral circulation so much in these situations in the ICU that people's fingers and toes actually die and they can fall off because of lack of circulation, and that's from these drugs. Another thing you see is that patients who are on pressors in the ICU oftentimes develop GI issues because blood flow is not shunted towards the gut. It actually removes blood flow from the gut. So people who have extended stress responses, or like in fight or flight responses, some of the things that people experience is that the immediate need to have a bowel movement, and then also there's it damages digestion, like they'll get bloated or have situations. That's because blood flow is rerouted away from the gut under stressful situations and moves towards those more vital, at least in these scenarios, tissues. So that's for the first one. The second one, where you see increased energy production through recruitment of substrates, when people are given synthetic glucocorticoid drugs, some of the things that you see, the most prominent things that you see for like a dexamethasone or a methylprednisolone, is hyperglycemia, so increased blood sugar. So there's your increased gluconeogenesis and your increased glycogen breakdown. You see hypertriglyceridemia, which is elevated blood lipids, particularly triglycerides, and then you see elevated cholesterol. So you're seeing that is the mobilization of substrates under the effect of these hormones. And so you can give people these compounds, these analogs, and you can get these same exact effects that they're discussing here that you would have normally in your body, although they're more amplified with the synthetic drugs because their metabolism has been altered, but they're more amplified under these under these drug situations, but it gives you a picture into what's going on. And then the third one is the optimized ATP availability to vital tissues at the expense of others. When you run like glucocorticoids and things like that, you can see a lowered testosterone production. like the dexamethasone and things like that, they can actually start to turn off gonadal production. The other thing that you pointed out is the low carb diets, like the low carb dieters coming out with like super low testosterone or decreased testosterone levels. That's one example. There's also numerous studies showing decreased testosterone and thyroid hormones in fasting situations. So you're lower and an increase in either glucocorticoid metabolism or glucocorticoids to some extent, as well as growth hormone and then the catecholamines. So you see increase in catecholamines, decrease in and an increase in glucocorticoids or glucocorticoid metabolism. That's important because it can happen at the cell with the 11 beta HSD enzymes. And increases in growth hormone, which also can help to release fatty acid substrate from tissues for oxidation. So all of these stress situations are, and then even using synthetic stress, stress hormone analogs, produce these same profiles. Like they're standard profiles that you see every single time when you use these drugs. You come in and like it's so standard that treatment pathways in the hospital, if somebody goes on certain steroid drugs, certain glucocorticoids, they automatically get blood sugar checks every 4 hours before every single meal and before bed, because the hyperglycemia, it's not necessarily that the glucose per se is toxic, but the like perhaps high concentrations in the blood on top of the elevated gluconeogenesis on top of the insulin resistance is toxic. So using insulin in those situations does actually have a protective therapeutic effect. They talk about it in this study. But it's just interesting because you can see that directly, these effects inside the hospital and working with any patients that are using any of these compounds.
Yeah, for sure. And insulin resistance you're mentioning, and they do talk about this in this article as well, I'm pretty sure.
Yeah, they do.
Is that is an effect of the long-term exposure to these glucocorticoids. And so, for example, we've touched on this, I think, in the very early on in the podcast. I know I mentioned it. I'm pretty sure we did. Discussing elevated blood sugar being extremely protective in rats exposed to high, very like potent stressors, where the ones that did not have elevated blood sugar beforehand would die when they were exposed to the stressor, whereas the ones that had the elevated blood sugar were protected. And this is not because these rats were diabetic and they weren't able to use the glucose well, and so it was building up in their blood and they were under really high stress hormones. Instead, they just had enough substrate available to deal with the stressor. And so that's the whole point of these stress hormones initially, is to produce enough substrate, create enough available substrate to deal with the stressor. And if they do that, they're super protective. Now, in the long term, though, then you start seeing elevated fasting blood sugar, elevated fasting free fatty acids. And that's a different story. That's not protective. Instead, that is happening as a result of long-term stress. For example, long-term glucocorticoid exposure, which we'll talk about again. I think they talk about in the study. And what happens when you have long-term exposure, again, I'm getting ahead of myself, but it just all comes together, is it inhibits our ability to respire. It inhibits our mitochondria's ability to produce ATP, and that leads to elevated levels of blood sugar and free fatty acids, not to increase energy production, but instead because energy production is blocked. And that is a pathological state. It's a part of the adaptive state. It's just a deeper part that tends to come with a lot of degeneration, again, because you have to favor the absolute most important vital tissues. But yeah, so I guess I'll kind of let us get there as opposed to jumping too far ahead.
Well, and they talk about it too. They talk about it down lower, that under the stress response, the mitochondria actually shift towards a higher fatty acid oxidation at the expense of glucose. I think there's a line that directly discusses that.
Yep, and there's blockages along the electron transport chain that mediate that. So to move forward here and get to that, they then mention that excessive or chronic physical as well as emotional stress can lead to significant dysregulation and or failure of the adaptive mechanisms and subsequent increased morbidity and mortality, such as cardiovascular disease, metabolic syndrome, immunosuppression, and depression. So again, kind of discussing what we were mentioning here, where over time, the more that this system is used, just like if we think of the general adaptation syndrome, the closer we're going to get toward that exhaustion, the degeneration, and the diseases, because we are in such a severe long-term energy deficit that we cannot take out any further loans. We don't have the resources available to do that, and we're in this huge debt. and eventually our bodies can't support it, and that's degeneration.
Yep. I know you don't have it highlighted on there, but there's a sentence in that next paragraph where they say indeed. It starts with indeed. And they talk about indeed over 90% of cellular energy generation takes place in the mitochondria. And in addition, mitochondria have important biosynthetic activities, control intracellular calcium metabolism and signaling, regulate thermogenesis, generate most cellular reactive oxygen species, and serve as the gatekeepers of the cell for programmed cell death. So the reason I want to highlight that there is because mitochondria are the main source of energy production in the cell, like all of these things have to happen through them. And then these other things that they're talking about, for example, important biosynthetic activities, they produce steroid hormones. They're the main site of steroidogenesis. The control of intracellular calcium metabolism and signaling is extremely important for the excitation and relaxation of the cell. It's what controls contraction, for example, in musculature, and a lot of the activating activities inside the cell. Regulating thermogenesis is, like, for example, infection with fevers, but also just in response to cold. And maintaining general body temperature overall is extremely important for enzyme function. Another one that's extremely important that I think we'll highlight in this study is generating most of the cellular reactive oxygen species. This becomes really important. We've talked about this ad nauseum, I think, in regards to, like, you want to have, and then we'll get into this in the study too. You want to have adequate antioxidants at the mitochondria to deal with the reactive oxygen species, but you also don't want to load your mitochondria with tons of polyunsaturated fatty acids that can interact with those reactive oxygen species. And then you want to have adequate electron flow and energy flow through the mitochondria to avoid an excess production of reactive oxygen species. So the reactive oxygen species question in the oxidative stress theory of aging strongly centers around the mitochondrial function and optimizing multiple pathways in that area. And then the last piece is that the controller of, and this is actually important for things like cancer, but also for general loss of structure, is that the loss of energy production at the mitochondria is the prime signaling function or event that triggers apoptosis. When the mitochondria stops producing ATP or produces an ineffectual amount of ATP, then it literally signals the cell to move towards apoptosis, and it happens through that mitochondria directly. So what's controlling the fate of cells as far as live or die is energy. So do you have enough energy? Yes or no? And then if no, apoptosis. If yes, okay, are there some backup pathways that we can establish if you're under stress to deal with that, to produce more energy? Or we don't need to go to the backup pathways because we have enough energy and we're functioning smoothly. But it's the switch is at the mitochondria, which I think is extremely important.
Yeah, absolutely. I agree. And in terms of the reactive oxygen species production, the other key thing there is we want to be doing that in the context of high ATP, tightly coupled mitochondria that will then lead to reactive oxygen species production and the beneficial adaptive responses to that, to a high energy state, as opposed to a low energy state. I'm assuming we'll talk about that a little bit more later on, but we've also dug into it in the hormesis series in the episode discussing the reactive oxygen species theory of obesity. And we also talked about, you mentioned aging in terms of reactive oxygen species and polyunsaturated fats. And so we discussed that on a series discussing aging. So I'll link back to all of those episodes for people who want to dig into those things in more detail.
Yep.
All right, moving on. I didn't have anything else to add here, just kind of this part talking about mitochondria being the mediators, producing energy to deal with the stressors. Was there anything you wanted to highlight here, Mike?
They just said that, and it's something that we already talked about, but that first sentence says, thus mitochondria are primarily responsible for meeting the enormous energy demands of the fight and flight response in vital tissues by oxidizing the large amount of substrates that are made available by stress hormone-induced mobilization from energy stores. So I already mentioned that, but essentially all it's saying is that the stress hormones mobilize substrate, and then the mitochondria have to throttle up their energy output and ability to mobilize substrate under the stress situations. And I highlighted this one myself specifically because when we talked about the fatty liver stuff and talk like the bottlenecks that happen in the mitochondria that induce fatty liver can be induced by, you can develop fatty liver with starvation. And when you have this, and it was somewhat paradoxical, but it's when you have this large amount of catecholamines and glucocorticoids releasing tons of substrate, then the cells in the liver, or cells in the body in general, have to meet that demand by throttling up their mitochondrial energy output. So it's not just, oh, we're releasing substrate, it's, oh, we're releasing substrate and then we have to burn it, or burn it in quotations, but that's, yeah, it's important that it's both. You have to add fuel, then you have to like use that fuel.
Mm-hmm. And when you don't, that's when you start to see insulin resistance and whatnot. And that's why in the fatty liver state, the fat in the liver is actually coming from our own fat stores that's liberated due to the stress response, the catecholamines specifically, that release fat from our fat stores. And then since we're not using it, the liver ends up storing it. So yeah. Just kind of a dig at people suggesting that it's mostly ingested carbohydrate or something like that. That's the cause. But we had a long 8-part series discussing why that's not the case.
Yes.
Okay. So moving forward, again, this is all things that we kind of discussed, as you mentioned, just general mitochondrial respiration as the response to stress that provides the energy needed to deal with the stress. But digging into some of the specifics of the stress response is what I wanted to get into here. And so talking about the glucocorticoids is next. And so they basically start by saying that glucocorticoids play a major role in survival during stress. Of course, we've discussed that, of course, is one of the main factors or main hormones produced in response to stress. And so here's some of what they do in order to mediate the response. So they state that modulation of mitochondrial metabolic activities by glucocorticoids is biphasic. This means there's 2 phases. Short-term exposure to stress concentrations of glucocorticoids is associated with the induction of mitochondrial biogenesis and enzymatic activity of selected subunits of the respiratory chain complexes, whereas prolonged exposure to glucocorticoids causes respiratory chain dysfunction, increased reactive oxygen species generation, mitochondrial structural abnormalities, apoptosis, and cell death, depending on the target tissue energy requirements and developmental stage of the organisms. So, just to put that into more clear English, the short-term exposure to glucocorticoids, which is basically cortisol, increases energy production to deal with the immediate stress. And also they mentioned it induces mitochondrial biogenesis. Basically, you're increasing various adaptive responses. One of them is creating more mitochondria to deal with future stress. That's what happens first. And then second, this begins to cause some issues. Instead of increasing energy production, it actually blocks energy production. They mentioned that it inhibits or causes respiratory chain dysfunction, increases the oxidative stress, and causes abnormalities and death to the mitochondria and to the cell. And they also mentioned that this depends on tissue requirements and the developmental stage. We're basically saying this depends on the larger context, but essentially, when you're under a prolonged stress state, the excess glucose production is one of the things, or excess glucocorticoid production is one of the things that will mediate this biphasic response.
Yeah. I don't have much more to add specifically to that. I think you covered it pretty well. I mean, it essentially, when you have an initial stressor, the glucocorticoids release substrate, and then the mitochondria have to respond by increasing energy output. But over time, like it's not maintainable, right? You have a organic structure that has to there's only so much substrate for you to oxidize. And then number 2, there's only so much ability for the mitochondria to increase number and then also to oxidize substrate. So there's a limit to what is capable there. So that initial response, you're like, okay, we're trying to meet the demand, but over time it's like, all right, we're not meeting this demand, and like we can't continue this level of output, and then it starts to degrade. What I want to mention here directly is in the yellow box above, they actually discuss this a little bit. And an example, because this is where you get some of people talk about some of the hormesis arguments. But when you get to the yellow box above, when they start on the bottom paragraph on the left-hand side, exposure, it says exposure to various stressors such as cold, fasting, and exercise activates PGC1 by several signaling pathways, including beta-adrenergic, calcium-2-dependent, nitric oxide, and AMPK activated protein kinase pathways. In addition to activating the NRF, the nuclear receptor factors, PGC1 alpha interacts with estrogen receptor related alpha and gamma peroxisome proliferated activated receptor, so PPAR alpha and gamma, and thyroid glucocorticoid and retinoid receptors, which together contribute to regulation of mitochondrial biogenesis and fatty acid oxidation. So basically, when you have these stressful situations with glucocorticoids and the stress pathway in general, PGC1 alpha, which is I think it's like a protein and a nuclear receptor that gets activated. It triggers all these other stress receptors to get activated, and then it upregulates mitochondrial biogenesis and then also fatty acid oxidation, which is important because fatty acids are one of the main substrates released. But what they continue to say is the significance of PGC1 transcription factor in regulating mitochondrial responses to various stressors is evident by the severe phenotype of PGC1 knockout animal models. So PGC1 alpha knockout mice exhibit important deficiencies in cardiac energy reserves and function and develop heart failure in response to stress. Interestingly, although cardiac-specific overexpression of PGC1 alpha promotes mitochondrial biogenesis, it results in reversible cardiomyopathy. So what you're seeing is that when you take the mice's ability to handle stress through PGC1 alpha out, then they develop heart failure, and because they can't muster enough energy to deal with an increased energy demand, so they can't deal with the stress. But when you overexpress the ability to deal with stress, you then also develop the cardiomyopathy because there's only so much energy that you can throttle and only so much mitochondrial function that you can so much mitochondria that you can produce and then have function appropriately. So it's very important to see that when you have a stressful situation, you want to muster up the response to deal with it. But if you do it too much, there's also a problem with that as well. So there's a narrow response where it's like, okay, you have the stress, you deal with the stress, and then you recover and you move on. But then if it continues, if you keep layering stressors on top and you have all these stressors, then you start to move into dysfunction. And from an overactivation of these pathways like PGC1 alpha, which is a main pathway that is often discussed in the hormetic literature, but is also often it's one of the main pathways through which these backup systems in the stress response work.
Yeah, 100%. This is one of, I think, the three kind of misnomers, misunderstandings that I think we talked about in the hormesis series that support, mistakenly support the idea of hormesis. And it's exactly this, where you have the adaptive response, as you mentioned, driven by stress hormones, activating all these stress pathways, nitric oxide, AMPK, PGC1 alpha, estrogen, and on from there, and induced by cold, induced by fasting, induced by exercise. And so you have this normal adaptive response that allows us to deal with those increased energy demands. And then they say, well, when you remove that adaptive response, now you get heart failure in response to a stress. So obviously, we just need more of that adaptive response. And they ignore that last part that you mentioned where, well, when you add more of that response, you actually get cardiomyopathy. And this happens in all the pathways where it's not about increasing the activity of these pathways. It's about making sure that they're actually functioning properly. When you get to a point where you can't adapt to a stressor, that is when you've gone way far down into that exhaustion phase of general adaptation syndrome, and you're in a really highly degenerative state. And that's what you see in degenerative conditions. In diabetes, for example, you're not able to activate autophagy because you don't have enough ATP production, among other things, because you've gone down these pathways for so long. So the goal here is not to increase PGC1 alpha expression or any of the expression of these other stress pathways, but rather to make sure that they're functioning properly, which requires adequate energy and requires not having too much stress. And if you continue to activate the hormetic pathways, you push farther down that place, like down that pathway into this state where you can't adapt any further. And that adaptation continues to come at further and further of a cost, or greater and greater of a cost, and then you end up with degeneration. So yeah, it's a great example here explaining that. And we talked through a bunch of others in the hormesis series.
Yeah, and they talk about, there's somewhere in this article where they talk about that some of these pathways, these adaptive pathways, are actually upregulated inside diabetes, despite so for example, when researchers discuss this, they often talk about it as a paradox. Because but these are beneficial. It's like, no, they're stress pathways. And so when you see it in diabetes, yes, of course you see it in diabetes. Of course you're going to see some of these things upregulated in diabetes because the diabetes is a chronic stress state oftentimes, and it's issues with energy production at the mitochondria, and then upregulation of the adaptive hormones, which we talk about it all the time, but it's just such a good example of what we're talking about.
Yep. Yep. Absolutely. Absolutely. So, was there anything else you wanted to add from this part?
No, the other stuff that I went into there is like way more specific. It's the last paragraph. It's way more specific. I think we should just go to the next step with the glucocorticoids that you're talking about.
Okay.
Did you highlight so you stopped, so you did that paragraph there, right? When you go down and it starts with indeed, that next section is actually really helpful to explain, because it talks about indeed short-term exposure of skeletal muscles to synthetic glucocorticoid dexamethasone stimulates transcription primarily of nuclear genes and to a lesser extent mitochondrial DNA encoded genes affecting mitochondrial function and biogenesis. No increase in mitochondrial transcription factor alpha or nuclear respiratory factor 1 and 2 expression was observed in these studies. So this was short-term exposure. But then they go down here and they say, in the next paragraph, it says, we recently demonstrated in a human mitochondrial gene-focused cDNA microarray system that there is a differential transcription response of multiple mitochondrial associated genes, including the gene encoding monoamine oxidase after short versus long-term exposure of skeletal muscles to glucocorticoids. This was accompanied by a time-dependent release of hydrogen peroxide and indicating increased oxidative stress over time. So in short-term response of muscle tissue to glucocorticoids, dexamethasone is a synthetic one that they discussed. The dexamethasone it increased the mitochondrial function and biogenesis so that the muscles can meet that demand that they had to meet, and it didn't actually increase the nuclear respiratory factor 1, so NRF1 and NRF2. It didn't increase those because it wasn't necessary. But in long-term production, in long-term exposure, you upregulated mitochondrial biogenesis and you upregulated mitochondrial function, but in doing so, it eventually depleted the muscle's ability to buffer the hydrogen peroxide that was produced under these different circumstances. And then it wound up causing oxidative stress. So again, that's showing that the mitochondria only there's a limit to the amount of throttling you can do at the mitochondria. And so that's something to keep in mind, is that balance. And that's where you see the difference between like a short-term stressful situation, for example, like exercise, versus and exercise can become a long-term thing, right? Like when you see in marathon runners, they have high amounts of oxidative stress following their events, versus if you had somebody who like went and did a lifting session, you may not really see strong increases in oxidative stress. So there's a limit to what the body and the mitochondria can handle.
Yeah. And you had mentioned earlier in that over time degeneration and on that a lack of substrate can be involved, but so can other factors that inhibit respiration and the usage of that substrate. And the vast majority of the time, it's not the limit in substrate, right? People die all the time with lots of extra body fat that they could have used. Instead, it's the capacity to use it and the various things that block our ability to use it. That really is why we focus on those things all the time. In addition, of course, to getting the substrate in. Obviously, if you don't have the substrate, you can't produce energy from it. But the vast majority of the time, the degeneration here is happening because there are other things that are blocking that energy production. And so, as you're mentioning here, that's part of why we see a contrast between short-term and long-term.
Yeah. And the other thing, too, to keep in mind is that when you have that elevated level of hydrogen peroxide and oxidative stress, those reactive oxygen species wind up causing damage to the mitochondrial structure. And that impairs mitochondrial functioning. And above, they talk about it in terms of like, there's a certain number of mitochondrial genes, because the reactive oxygen species damage the mitochondrial DNA. And then essentially that after a certain threshold is reached, the mitochondria basically have to undergo apoptosis because they're not functioning anymore, because they lose their ability to produce ATP. So you have that happening over time. The other thing that's important, specifically with the body fat thing that you discussed, Jay, is, and we've talked about this in one of the previous studies that we looked at, was that the body fat in the obesity situation is not an excess of energy. It's a shunting of substrate to fat storage because of issues with energetic output. So and that's an example of that. The actual problem is what's going on with energy production and not necessarily a substrate issue per se. And I mean, it depends on like if you consider like PUFA a good substrate, right? But there's it's important to look at what's happening not only with what's coming in, but you also have to look at the energetic production side, and that's where I call it the calories in, calories out equations become problematic, and it's also where some of the ideas of caloric restriction for longevity become problematic, among other reasons, right? And they kind of talk about this later on in the study, the caloric restriction stuff, but we've already discussed like the different monkey studies with the refined food diet versus a whole food diet with caloric restriction, and the researchers trying to argue that the whole foods diet was just more hormetic than the refined foods diet, but it was really like a question of less crap. So I won't continue on that, but yeah, I think that those are good examples in questioning some of these ideas.
Yeah. And there are a ton of very clear confounding factors that fly in the face of the calories in, calories out model. So I'll link back to when we've discussed that. And yeah, you mentioned the reactive oxygen species potentially causing oxidative stress, and they certainly can. Of course, when our adaptive processes are working well, one of them is uncoupling, which we'll get to in a second. That shouldn't be happening too much. And a couple of things that are very, very protective here are ATP and carbon dioxide. And this is part of why producing reactive oxygen species in a high energy, high ATP state is very different from a low energy state. And a low energy state being one that's much more prone toward destruction and damage of things like DNA, protein structure, fats, and on from there. And of course, as you mentioned too, if you have a lot of polyunsaturated fats, that'll also increase your susceptibility to oxidative stress from the reactive oxygen species.
Yeah, and even just nutrient repletion, right? If you have the raw material to make glutathione, and you have the raw material to allow manganese superdioxide dismutase or catalase and these different enzymes to function appropriately, they help to minimize the effects of the reactive oxygen species. They essentially quench the reactive oxygen species even in situations where you don't have that adequate energy. Although these enzymes do also require energy. So there's multiple factors to have here, right? Like you want to have a high energy output, but you also don't want to have a delicate structure that would be damaged by ROS, which would mean high PUFA in the membrane. And you also want to have the ability to clean up that ROS. And that's where you see some of these other enzymes and antioxidants like vitamin E or vitamin C or some of those things come into play and become important in making sure that your diet is on point. And a lot of this is your diet on point, because all of the more minute details wind up becoming a function of what are you doing macroscopically as far as diet and lifestyle, etc.
Yeah, and I would say that in the vast majority of cases, it's not that you just don't have enough glutathione. Like, I think it's very rare that that's the issue, and it's not like you just don't have enough cysteine to produce glutathione. Like, I don't think the main issue people are having is that they're walking around with the cysteine deficiency. Of course, there are circumstances where that is a factor, and there's circumstances where there might be something very wrong with those antioxidant systems, but I think those tend to be more surface level and reactive to the problem in the first place, being issues along energy production pathways leading to way excessive oxidative stress due to reactive oxygen species production in a low energy state, activating the stress pathways excessively, and on from there. I think that for the most part, the focus on the antioxidant pathways is misguided, I would say.
What I'm saying is it's a whole picture. Like there's multiple angles to hit everything at. So you want to have adequate energy output. You want to have your minerals in place so that you have those enzymes functioning appropriately. You want to provide the raw material for them. You don't want to have high amount of PUFA in the membranes. There's multiple elements to keep in mind when you're looking at the ROS picture and the damage from them. And it's not just like these adaptive pathways. Like there's multiple pieces to look at.
For sure. All right. So moving on to the chronic effects, more specifically of the glucocorticoids. They discussed that the clinical studies on the effects of chronic exposure to glucocorticoids have shown increased lactate production after aerobic exercise produced by anaerobic glycolysis owing to mitochondrial dysfunction, along with decreased complex 1 activity and oxidative damage to the mitochondrial and nuclear DNA in skeletal muscle. This is what we were just discussing, where you see increased oxidative stress when these pathways are being activated increasingly over time, and you see inhibited energy production leading to low ATP, and then because of that, a forced reliance on glycolysis, leading to excess lactate production. And this is why I picked this study. It's just everything all coming together beautifully, right? This picture that we kind of discuss all the time. We talked about it, and this is why we keep referencing all these past episodes too, because it all just goes right hand in hand. We talked about it before in terms of our carbon dioxide series, the problems with it being in a state where you're producing a lot of lactate. And interestingly, just as a kind of side note here, we talked about people who are more prone to excess lactic acid production in response to stress being they're more prone, more susceptible, or more vulnerable to panic attacks due to excessive lactate production. And they're saying here that chronic glucocorticoids create that state. So that's, of course, something to consider as far as why somebody might be more prone to that sort of response to stress. But yeah, it's just very clearly showing everything, like how this applies to everything. We talked about it in terms of how this can lead to a cancer state as well, where you're basically in this sort of state where you're seeing excess lactate production, not able to fully oxidize substrate, and leading to this sort of degeneration. And I'll just finish out this quote and then let you go, Mike, where they mention that glucocorticoids also increase oxidative stress damage to neurons, both by increasing glutamate and calcium and by decreasing antioxidant enzymes, specifically in the hippocampal neurons. And then they finish up by saying that these findings indicate a primary pathogenic role of mitochondria and reactive oxygen species in glucocorticoid-induced tissue damage. So saying that this is the pathway, these are the pathways through which chronic cortisol exposure causes damage to our tissues. And just, again, highlighting increased glutamate, increased calcium. These aren't things we focused on too much, but I think we talked about excess glutamate maybe in our sleep series. But again, these just being the hallmarks of excess stress, low energy states, where you're seeing high amounts of intracellular calcium coming in, causing all of the mineral dysfunction that we discussed in the series discussing blood pressure and the regulation of electrolytes there. And excess glutamate being a driver of excitotoxicity or excitability in all cells, but especially in the nervous system. Just kind of all coming together to create this cohesive view, this cohesive picture that we always discuss. And it all fits together, basically suggesting that stress is not your friend.
Yeah, and they also go in here and they talk about the oxidative damage that happens from the glucocorticoids, again, that they cause damage to the mitochondria and then the nuclear DNA in skeletal muscle. And then the other thing they talk about is, interestingly, antioxidant compounds and enzymes can prevent glucocorticoid-induced mitochondrial DNA damage in apoptosis in skeletal muscle and vascular endothelium. So they're showing that having those adequate things are helpful. But the other thing I wanted to highlight here is that the glucocorticoids also cause issues at the vascular endothelium. We've talked about how elevated cortisol and also aldosterone in the RAS system can cause oxidative stress inside the vascular endothelial cells and the smooth muscle cells of your arteries and whatnot, and lead to atherosclerosis themselves through these same pathways. Another thing that you don't have highlighted here, but I wanted to touch on, is they say glucocorticoids are important regulators of T cell growth, differentiation, and apoptosis. Disruption of mitochondrial integrity is known to be associated with glucocorticoid-induced T cell apoptosis. This process is tightly regulated between pro-apoptotic and anti-apoptotic BCL2 family members, resulting in the activation of BAX and BAC2, opening of the mitochondrial transition pore in the outer or permeability transition pore in the outer mitochondrial membrane, and release of cytochrome C in the cytoplasm. So the reason I wanted to mention that one is that it's basically showing here that in conjunction with causing damage to nuclear and mitochondrial DNA inside neurons, musculoskeletal cells, and the vascular endothelium, the glucocorticoids are also causing apoptosis of T cells, which are immune cells, and that is largely their mechanism for anti-inflammation, is its immunosuppression. So the glucocorticoids are destroying the T cells when in the chronic and high exposure, and then it's like, yeah, you don't have inflammation now because you have no immune response.
Right.
So you have like this destruction of musculature, this destruction of neurons through hyperexcitability, and this destruction of vascular cells on top of immunosuppression. So increased risk of infection, et cetera, et cetera. And that's known from using these drugs. There's studies, you can go on PubMed and you can type in like glucocorticoid mania or glucocorticoid psychiatric effects. And you see like there's literally studies talking about like using synthetic glucocorticoids and inducing mania, inducing insomnia. Both of those are indications of hyperexcitability in the brain with elevations of glutamate. You can see, like, look at studies of aldosterone, which is a mineral corticoid, but also can activate the glucocorticoid receptors. So you have aldosterone and also the glucocorticoids inducing atherosclerosis. You can see people taking glucocorticoids over an extended period of time for inflammation, whatever it is, like, or in cancer situations, they give glucocorticoids to deal with the inflammatory response. And then those can lead to atherosclerosis, diabetes, etc. And then also the glucocorticoids cause wasting of musculature, and because it's taking the musculature, breaking it down, turning it into amino acids, and then using that for gluconeogenesis, and then producing abdominal obesity. And then you also see in the research, you also see increased risk of infection with the use of glucocorticoids. So you see people are at high risk for developing infection. And one of the side effects of glucocorticoid drugs is thrush, which is an infection of candida inside your oral cavity, which you should not get as an adult. And usually you only see that for a brief time after periods of high antibiotic use. So overall, they're like elevated glucocorticoids, either high amounts or extended use, basically just slowly degrade your body in order to fuel this adaptive response. And the adaptive response, or I guess you don't like adaptive, but a stress response that is fueling over time is like you're creating this output to deal with this situation, but it's coming at a huge cost to your body. It's literally degradation of structures on multiple levels.
Yeah. Yeah, and just to mention a couple other things that tag into what you were saying. So the immunosuppression driven by cortisol and glucocorticoids as their means of being anti-inflammatory is extremely parallel to what happens with estrogen and what happens with omega-3s. Both of them have the same effects where they are anti-inflammatory by immunosuppression. So you get those short-term benefits, long-term costs. And one of the side effects there as well is also a shift toward autoimmunity, increasing autoimmune states. So yeah, and that's something we discussed in our autoimmune series. But yeah, I wanted to throw that in there. You mentioned insomnia with the excessive glucocorticoids, partially because of their increased glutamate activity and increased calcium influx, which they mentioned. And if you want to see that in action, go on a low carb diet, go on a carnivore diet, go on a keto diet. I have to say that insomnia is probably one of, if not the top symptom I see from people on those diets. Of course, driving glucocorticoids and catecholamines is a great way to cause a state like that where you can't get into a physiological relaxation. That's why it's basically the same as having coffee in a fasted state. It's like you're just running on these fumes, you're running on these stress hormones, and it comes with that insane excitability. And that insane excitability also can, and I've seen this a lot too, causes increased reactivity to all sorts of things that can increase allergies or allergic responses to foods, and drive like the mast cell activation syndrome. People who are getting histamine responses, oxalate issues, or just random responses to different foods, chemical sensitivities. That also is something I see quite a bit from people who have driven down these pathways for extended periods of time. And again, things like excess glutamate and calcium being factors there. And you mentioned the increase in aldosterone that happens here. And again, something we discussed in the blood pressure series. Again, just being one of the factors here that allows for the response in terms of circulation and blood flow, and also for the stress response in turn, it helps to maintain our blood volume when we're under stress, because the sodium starts going into the cells, and so we're losing it in the blood, and we end up with all the swelling and everything. So we're losing blood volume because of that as well. All of that just being a direct response of energy failure, and that's what we're seeing here. And I don't think they talk about sepsis as much in this study, but there's another study too that I was thinking about going over where they show that this is exactly what's happening in sepsis, basically extreme energy failure and all of the side effects, so to speak, or direct effects of that. And the only other thing I wanted to mention here before we move on, well, there's actually two things. So one is that I know I was alluding to how all of these effects of chronic stress are what you see if you're going down the hormetic pathways. And again, we talked about this in the hormesis series, but I know some people might be thinking, well, I'm not talking about inducing chronic stress. I'm just talking about inducing acute stress a lot, all the time with, a ketogenic diet and then exercise and then jumping into cold water bath, cold
And Wim
thermogenesis,
Hof breathing.
and then doing Wim Hof breathing. It's like that is like chronic stress doesn't mean that you're literally always like fully 100% of the time under stress. You know, someone who's in a chronic stress state like might have some reprieve when they're sleeping or in between bouts of stress or responses to stressors. But those acute stressors do still all add together to drive the exhaustion type state that we talked about in terms of general adaptation syndrome, where you never get back up to baseline. You keep going lower and lower and lower unless you're focused on doing the opposite of reducing the stressors and increasing our capacity to deal with them. And so it's not a matter of just forcing the acute stress and not the chronic. The acute stress still is the major cost that is leading to the need for the chronic stress response. The reason why you get chronic stress, like this sort of response, when you go through acute stress for too long, is because that is acute stress response is extremely costly. Like it is the problem that leads to chronic stress. Like they aren't separate. One is just an extension of the other. The chronic one is just an extension of the acute one. Of course, I'm not saying we can also always avoid those acute stressors, but as we talked about earlier, it's a matter of recovering from them, preventing them from being too intense, making sure they have beneficial specific effects that are worth it. Again, that all goes back to the hormesis question, but or not question, but discussion. And so I just wanted to throw that in there for anyone who might be still clinging to their acute stressors that they like to induce.
Yeah, everything's cumulative, and it can't not be cumulative because, and this is the importance of Selye's general adaptation syndrome, is it's general. The response to stress is general. So every time you induce stress, you have a general response, and you like it will accumulate on the system. That's why the authors can be like, oh, exercise, fasting, and cold exposure. It's like those are three entirely different things, but they still generate the same responses at the cells. So if you're gonna do all of those, like yes, okay, you can exercise. Okay, fine, you're exercising, great. Okay, now you're gonna fast. Okay, now you're gonna go do a cold exposure. Well, now you have now even though they're individual stress responses, they're cumulative on the system. So it's like, how much can your body handle with that? And like,
what's the cost of handling
What's the cost exactly?
Like even if you're just doing enough that you can handle without it being a major cost immediately, even if you're doing that one thing every day, that's still coming at a cost. It's just not as big of a cost, so you don't see it as soon, but still a cost.
Yeah. And then what happens if you're doing your fasting, exercise, cold exposure, and then something terrible happens in your life? Like, how equipped are you to deal with that stressor? I would say there's decreased level of ability to handle, and you see that with people. You see that with people who undergo extended periods of like doing the fasting over extended period of time, and then the cold exposure. And you hear like one of the people I work with is saying, yeah, I worked out and I fasted, and then like I didn't really get much sleep one night because of this and because of that, and then the next day I took a cold shower and bam, I got hit with the flu. I did the not the cold shower, the little cold chambers that you go into. And he's like, bam, I got sick right after. It's like, yeah, of course you got sick right after. What do you expect? You just literally just put yourself through the ringer, and then you've like lowered your defenses to deal with life. It's like, I'm going to stress myself in these other areas because other areas of life aren't stressful enough. So when I finally get exposed to it, I'm crippled. It doesn't make any sense.
Yeah. And you know, one of the things I want to mention here too is when you're in that resistance phase, the high stress hormone phase, first, you are more resistant to stressors because you're already stressed. And that was what the Wim Hof study showed. It's like if you create stress ahead of time with Wim Hof breathing or cold thermogenesis, you know, specifically I think they were doing Wim Hof breathing, causing hypoxia, causing a low energy state,
metabolic alkalosis, and then elevated. They're blowing off all their CO2, and then they created a state of metabolic alkalosis, which caused a massive spike in the catecholamines, and then I think blood lipids followed, and they didn't respond strongly to LPS. It's like, yeah, of course you're not going to, because if you like, what do you treat people with and sepsis with? Catecholamines. So you're like preloading yourself with catecholamines before dealing with an endotoxin exposure. Of course you're not going to have a stress response to it now because you already have the stress response.
Right, your body already created the medication.
Yes.
As it's supposed to when you cause stress. It's Yeah, exactly. All right, I think we've hammered that point home. But
we beat the horse. The horse is super stressed now. It's bruised. We'll leave it alone. Well, we're gonna like give it some orange juice and treat it real nice.
Yeah. All right, we are going to wrap up that episode there and pick back up in part 2, where we'll be discussing why uncoupling is harmful in certain contexts and how the polyunsaturated fats, or PUFA, cause constant low-level uncoupling. We'll also be discussing the involvement of uncoupling, mitochondrial biogenesis, autophagy, heat shock proteins, and hypoxia-inducible factors in the stress response. We'll be talking about how stress prevents our mitochondria from effectively producing energy. We'll be talking about how chronic stress can cause insulin resistance, high blood pressure, weight gain, depression, and cardiovascular disease. We'll be talking about how sugar and fat cravings result from stress and why listening to them is beneficial, as well as how adaptations to stress get passed on through generations. If you did enjoy this episode, please leave a like or comment if you're watching on YouTube. And if you're listening elsewhere, please leave a review and 5-star rating on iTunes. All of those things really do a lot to help support the podcast and are very much appreciated. To check out the show notes for today's episode, head over to jfeldmanwellness.com/podcast, where you can take a look at the studies and articles and anything else that we referenced throughout today's episode. And if you are dealing with any low energy symptoms, maybe these are related to some of the different chronic health issues that we mentioned today, or if it's other low energy symptoms, things like chronic cravings and hunger, low energy or fatigue, chronic pain, weight gain, digestive symptoms, brain fog, poor sleep, hormonal imbalances, or various other low energy symptoms, then head over to jfeldmanwellness.com/energy, where you can sign up for a free energy balance mini course, where I'll explain how these different symptoms and conditions are really caused by lack of energy, and I'll also walk you through the main things that you can do from a diet and lifestyle perspective to maximize your cellular energy and resolve these symptoms and conditions. So to sign up for that free energy balance mini course, head over to jfeldmanwellness.com/energy. And with that, I'll see you in the next episode.